Let's see here. Good morning, everybody.
Good morning, Dr. Terrell.
Hey.
Good morning.
Good morning. Oh my gosh. So, let's see here. Just get situated here. So, good morning, everybody. I just wanted to show you something. Hopefully, didn't mess it up. But if you have a diffraction grating, that is like basically a diffraction grating. I have a whole bunch of them. I don't know where they are, but they're pieces of film, and they're actually set up like slides, like we used to have in projection cameras. You guys are so babies. You're all babies. You don't know.
I know cameras.
Yeah, I know. They're babies.
Hi,
But-
Professor.
Yes, Van. Good morning. So, but the diffraction gratings typically have, there's just a bunch of, they call them rulings. They're basically lines that are etched into the surface, and they're all parallel, you know? And they have a very consistent spacing value, D here. I didn't draw it consistently there, but it's supposed to be consistent. And you can, if you take light from this direction and you collimate it, get all the rays going the same direction, then you direct it onto this grating with spacing D, then you simply observe it at a different angle. Then what you will see is you will a series of wavelengths. Actually, the first one of which is at delta lambda equals d cos theta. And so this is like the sort of a basic incarnation of the grating equation. And so the way that gratings work, or the way that probably we're going to go over this again, I hope anyway, but the way that the monochromator works this is the machine that takes polychromatic light or white light and turns it into single color or single wavelength light, right? They work on this basis, and they typically use reflection gratings. And there's two serial processes like this. So there's an angle of incidence, and there's also an angle of diffraction, and you add them up. And so what that comes out is that D sine I plus sine R is equal to n lambda. And n, D is the spacing. I and R are the angles of incidence and observation. And then N is the order. And so, and then lambda is the wavelength. So so the order is the number of wavelengths. That have slipped. In the diffraction process. So for example, if you have one coherent wave like this, and then another one that was with this, but then we've changed it such that it's now like this. This is a case where this delta lambda here or actually this is not delta lambda, this is delta, let's just call it delta here. This is the path length difference. Between ray 1 and ray 2. And when this delta value, let's say that when this delta value is equal to n lambda, an integral multiple of wavelengths then constructive interference occurs. Oops, occurs. And you get, and basically and then that wavelength is bright. And then similarly, if you have n plus 1/2, then that makes a dark condition. Right? And so there's this equation up here is called the grading equation, and that one will guide you on setting your wavelength. Right? Normally, what you'll do is you'll rely on the fact that this has been done extremely carefully in the past with certain elements. Like, for example, you could have a hydrogen emission lamp or a neon emission lamp or something. Neon is cool because it has a lot of red lines, right? Yeah, and you can find one of the wavelengths, get it into first order, and then you can know I and R, right? Or at least you can know the sum of sine I and sine R, right? And then so you can use a calibration lamp. And then, and then, you know, the I and the R values, you drive these mechanically. Or you set up the optics such that they fall at a different place onto an imager. Like you could have a like you guys probably aren't even used to the idea of single photon detectors or single detectors of light, you know, because everything's a camera nowadays. Everything is a two-dimensional array of detectors, you know. But to do spectroscopy, you really just need a one-dimensional array. So let me just, I'll kind of try to move on here. I'll try to move this up to the top here. But what so the way this looks is that there's some light source, right? This is a light bulb. And then this light bulb is collimated. And then it's focused onto the input slit of a grating here. So the rays then come in like this, and they are recollimated, and they are directed onto a grating. And then the grating has a particular takeoff angle, right? So the grating, you can basically put the grating onto a rotational axis. So it rotates, and you can change angles I and R simultaneously. And then these guys, then they're refocused onto a detector. Normally there's a slit here too. This is called a slit. There's a slit here too. So that's some pretty phenomenally shitty artwork. Hopefully it doesn't completely obscure the point.
Terrell, where does the sample go?
This appears to be completely sample-free spectroscopy. That's a very good question. Very good question. Where does the sample go? So Actually, the sample would probably go, you would probably want to, you could put the sample actually pretty much anywhere. You could put it here, for example, or you could put it anywhere that it could catch the whole beam, or you could put it out here, you know. The difference, the preferable place for it actually is here. Oops, sorry. Because at that point, you'll only be irradiating the sample with one wavelength of light at a time. So for example, if your source has ultraviolet and visible and, you know, say near infrared light, has a broad range of wavelengths, and you irradiate that your sample with ultraviolet light, you can start to damage it, you know. So, you know, it depends on the molecules in there, right? If you have, you know, something I don't know, just making this up, but like you can photo bleach the molecules in there. I don't have direct experience with this, but I understand that it's better to have it on the sample side. On the other hand, there are many, the more popular, the more common type of spectrophotometer nowadays is called they're called CCD array detectors. And with CCDs, you actually never you have no exit slit. And with CCDs, what you'll have is an array of detectors. And and you just arrange it such that the array detector is set up on the focal plane of the monochromator, such that at each point on the detector, there's a different I and R value represented, right? So, and they'll change smoothly, right? And so what you'll have is, you know, lambda. So this might be the blue, you know, and then this might be the red as you go to larger angles, you know. And so each pixel then will have a different color. You can plot the intensity versus the pixel number, and then you can see a sort of a spectrum there. And this will be just like light power. Spectrum. And then you'll have to do some magic to convert it into power versus wavelength, you know. And sometimes it could be real straightforward. It could be just like a pixel number corresponds to wavelength, but normally there's a little bit of distortion. So,
Dr. Terrell?
yes, sir.
Are you saying that the CCD discriminates different wavelengths, or are you saying that like it's still spatially, it's like still using space to determine what the wavelength is based on the diffraction?
The latter.
Oh,
so
okay.
you know, it's an interesting point because, you know, most CCDs that we know of are color CCDs, right? And so they have this sort of weird, like at every point they can tell you what color it is. but that's actually a bit of an illusion. They can tell you the color, but they can't tell you the wavelength.
Oh, is it because they're simulating that color?
Yeah. Yeah.
Oh, okay.
They measure, they have three filters, a red, a green, and a blue, or a cyan, a magenta, and a CMR, and then something, CMY, and then RGB. Anyway, they have three colors, and they just like reproduce those colors on the screen, and they add them together, and our eyes can't tell the difference, But um, but if you want actual wavelength discrimination, then you need a monochromator. You need to have this set up such that you have collimated white light here. And then here you'll have collimated monochromatic light. Right, that'll be coming out. And then if you have an array detector, then each different angle, this will be, like this could be like 29.5 degrees, and this could be 35.3 degrees, and this could be, there'll be a range of angles, of takeoff angles from the grating represented on the detector.
Okay, got it. Thank you.
Yeah, cool. Does that make sense to, for example, that makes sense to Jonathan?
Dr. Terrell,
Yes, Fook.
for creatine rotors arrow change. So what do we, is that an abbreviation for gradient? I'm not sure if I read it correctly though.
I think you're looking at grading.
Oh,
Yes.
grating.
Yes, what that means there?
Creatine?
Yeah, grating, and then GRATINL. Under the picture, collimated.
Oh. You're trying to decompose my hieroglyphics. Where are we? Here?
Left, more to the left.
Okay, this is light. And
Yes.
this is grating.
Yes.
Rotates.
Yes. Okay.
And changes. Oops. I and R, the angles I and R. Angles I and R, I kind of defined them above.
Mm-hmm. Okay. What is grating in this case?
Grading. The grading. The grading is. It could be a flat piece of aluminum. It could be a flat aluminum mirror with a series of parallel lines of even spacing just scratched into it, for example.
Flat aluminum mirror. That is what? That is what, may I ask?
That has, for example, let me draw you a grating. Here's a flat. Oops. Here's a piece of flat real estate here, right?
Yes.
And this could be like a piece of glass, right? And then there's an aluminum coating on the surface. And then in that coating, there are a series of parallel, they're actually called rulings. And these rulings, they serve to diffract light. So I'm not in my office, right? But I have a ginormous diffraction grating. It's about this big. It's like 4 inches long. It's on a big old inch thick block of glass, and it and what I have the students do normally is you turn it such that you're looking along it and you're looking across the rulings, and then you look at the reflection of the fluorescent tubes above you, and you'll see like a red tube. Then right next to it, there'll be a green tube, and there'll be all these, maybe like the same tube reproduced in different colors. What is that, But that's because the tubes are emitting these discrete colors. That's another trick of the light on our mind, is that fluorescent tubes don't emit white light. They emit a series of monochromatic light beams. And if you use a grating, you can see that there'll be like 7 different copies of the tube in different colors. And so that a grating it's basically, you can actually make a grating too. You could just take a smooth surface, like it could be glass or anything, and take a piece of sandpaper and just whoosh, just scratch it with sandpaper, and then look at it, and it will diffract light. It won't be perfect, but you can do that. Anyway, I digress a little bit, but it's an important question, like what is a grating and how do these things work? And this is something that Harris has almost no information on. The book that we used to use, the Scoob text, is very good on this one. But the idea here, and I'm probably going to be totally embarrassed because probably the next chapter has all this stuff in great detail, and I'll have to go back over it or something, But the
And Dr. T,
yes, Funk.
for how you write I 29.5
Yes.
and then DET. What is that stand for, sir? Sorry, I didn't catch it.
Oh God, this is detectors.
Detectors. Got it. Got it.
Okay, cool.
Thank you, sir.
So okay, I've probably exhausted my ability to say anything meaningful here. So let's go back to the text here, and maybe we can get on with things. So so Beer's law here is A equals epsilon BC. So A is this logarithmic composite of the light power transmitted through a sample and through a blank. And epsilon is a molecular property. B is the path length, and C is the concentration of those molecules. Right? So now we've already kind of gone over this, and we will retouch on this, but absorbances are additive. That's all that means, really. And So here is, transmittance is P over P naught, A is minus log T, and A is epsilon BC. So C then is A over epsilon B is equal to minus 1 over epsilon B times log of T. And that's also equal to minus 1 over epsilon B log of P over P naught, right? And so remember that P is the light transmitted through a sample, and P naught is the same light transmitted through a blank. So let's see here. So let's do this. Let's do this little problem. We can see if I get it right. So find the absorbance and transmittance of a 0.00240 molar solution of a substance with an absorptivity of 313 per molar per centimeter in a 2 centimeter path length cell. I had to have a 2 centimeter path length. Okay, yay. Well, I really can't turn that light off. So A, oops, no, I've got to write this stuff down. Hold on. See, A is equal to 0.002. Oh no, this is C. Concentration is 0.0240. And that's molar. Epsilon is 313 per molar per centimeter. And B, the path length is 2.00 centimeters. The question is, A equals what and T equals what? Okay. So the easiest one here is A, right? Because A is equal to epsilon BC is equal to 313 m minus 1 cm minus 1 times 2 cm times 0.00240 molar, right? And let's see, this is going to be 313 times 0.0024 times. This absorbance will equal 1.50. There's a 2 there, right? And so now transmittance here will equal 10 to the minus A, right? Because A is equal to minus the log of T, and then 10 to the minus A will equal T. These are inverse functions, right? And so this will equal 0.03145. So that's how we do that. Let's see if I got it right.
Either you got it right or we both got it wrong. I got the same things.
Okay, good. Let's see here. 316. Okay, well, we're really close anyway. 1.50, right? Anyway, so there we go. And so this means that at this absorbance, only 3% of the light is transmitted through the solution. So it's then whether or not that's acceptable for you for quantitative purposes depends on how much light your spectrometer produces at that wavelength, right? So, you know, let me go back here to the page here. We can say that, let's say that you look at the power spectrum, and this is just P versus lambda, say 200, say to 800 nanometers. And say at 200, you've got a little bit of light here. And let's say this is the power spectrum of your lamp. Right? And then you're to ask yourself, well, can I measure uh, 2% of this wavelength? And the answer is probably yes. I mean, like if you're going to go up to say a peak wavelength here, and you're measuring this much, right? This is, say this is P0, right? Then let's say you have an absorber with a strong band there. Then this is the P spectrum. And this is the P0 spectrum. Then what we can do is we can make an absorbance spectrum here, right? Which when these are about the same, the absorbance will be 0. But here, this is the negative log of P over P0 right there, yeah? And so all I've done is that at every wavelength, I've taken these two values and I've computed the negative log and I've plotted it there, you know. Then at this wavelength here, you know, there's P is much smaller than P0. Let's say it's a 0.01. And this is going to equal 2, right? So this would maximum out here at about 2, right?
Dr. Taro, what are we taking a P and then absorbance, spectrum and absorbance at the same time?
Yeah, yeah, we're taking a blank, a P0 spectrum, right?
Yes.
And we're taking a P spectrum. You know, we're taking both these measurements, but we're taking the measurement at a series of wavelengths. You know, so we're taking this, you know, at 200 and all the way up to say 800 nanometers.
Mhm.
You know, and this could be say, you know, I don't know, 400 nanometers. You know, and so this is just a sort of like, this is stuff that we normally don't see. You know. Now, these are mostly kept internal to the instrument.
Dr. T, I have a
Yes.
question. If
Yes.
we have the absorbance range from 0.5 to 2, and it outside the absorbance range is inaccurate because of the transmission, or the range is too far away from the range that we have?
Right. So let's look at that. Let's look at that very question. That's a perfect question, right? So the question is, when is absorbance accurate? Right? And the answer really is when P and P0 are accurate, right? So for example, at this point here, there's probably a fairly significant amount of noise. So if I were to draw this a little bit more realistically, I would probably draw it like this, where there was some noise here. Does that make sense? So normally when you make a measurement, like if you take, say this number is like 1 and this number is 0.01 or something, you know. So well, actually this, you know, maybe 0.015 and 0.013 or something, you know. When you look at this last digit here, it's probably going to fluctuate from measurement to measurement. It's going to be a 5, then it'll be a 2, then it'll be a 3, then it'll be a 7. You know, the very last digits tend to fluctuate, and that's just the nature of all measurements. So if you then take the ratio of any snapshot of that, it might be a little high or it might be a little low. And what that tends to look like is that it looks like an up and down sort of a, it's called noise. And this noise is a fluctuation or a change, a random change in the absorbance signal that you get as a function of wavelength, right? And so long as the light power level is low, so this is where the light power is low, right? Then there's fluctuation, and that means that there's noise. Oops, sorry, there's noise in the absorbance. Just ignore that line there. There's noise in the absorbance. Does that make sense?
Yeah, but it's not it's inaccurate when you go outside the range, but
Right. Exactly. So this noise, so there's, there's really two. So the upper limit of absorbance greater than 2 being inaccurate, that has to do with the value P, right? Because when absorbance is greater than or equal to 2, then P is less than or equal to 0.01 times P0. Does that make sense? So this is, remember here you've got absorbance and transmittance. You've got 3, 2, 1, 0. And this is you've got, that's the relationship between absorbance and transmittance. So when the absorbance is greater than 2, then the light power that reaches the detector is less than 0.01 times P0.
Yeah, but the reason is inaccurate, and you reject it because of the noise interfere with the absorbance or interfere with your
Exactly. So if so the question here is, can P be measured accurately? Does that make sense? So if the smaller a signal is, the harder it is to measure it.
Okay.
That makes sense?
Thank you.
Good. Excellent conversation. And so then on the there's also another thing though that can make your measurement inaccurate, which is if P0 is small, right? So here P is small. And here P0 is small. Right. And so both are bad, both are generally bad for making absorption measurements, right? And then if P is small, that's also bad. So we actually touched on a bunch of stuff here, We talked about monochrometers. We talked about the diffraction of light over a series of wavelengths. Now we're starting to talk about the detection of light to measure concentration, right? And, you know, normally you would think that an instrument manufacturer would have some built-in safeguards, right? You know, something like a company like Varian or Thermo Fisher or something like that, that they would have the smarts, you know, to say, okay, engineers, if this signal is fluctuating a lot or it's changing sign or something weird is happening, then flag that data or don't display that data or do something to tell the poor user that something has gone terribly wrong and they're not supposed to trust this data, right? Do not transform this absorbance into concentration because the concentration will be wrong, right? You would think that an instrument manufacturer would have the common sense and the courtesy and the brains to do that. But they don't. They absolutely do not. And you can see it across all types of instrumentation. There is zero safeguards. There are zero safeguards for you as a user, you know? And there's all kinds of cases where signals are proportional to concentration, even NMR, you know? The number of protons is proportional to the integral of that peak, right? You know? And FTIR, the number, you know, the concentration of a species is proportional to the height or the integral of a particular absorption, right? And in UV vis, it's the same. And in fluorescence, it's the same. You know, the height of a peak is proportional to the amount of that stuff. You know, but it's all on you as a user to figure out if these values are accurate. And I'm not saying that's a good thing or anything, you know, but it keeps me employed, right? Because there's no safeguards. Absolutely nobody does anything. Not a single instrument maker has any measures whatsoever to prevent you from turning an instrument signal into junk data. Like it's, you know, garbage in, garbage out. Have you ever heard that expression?
Oh yeah.
Yeah. So
We're
if
keeping you on your toes.
Right. They actually very needlessly keep us on our toes too, you know, because they have no safeguards whatsoever. So so the lesson here is beware of garbage in, garbage out.
Wait, Dr. T?
Yes.
Sorry for my questions.
No.
So for the be aware.
Yeah. No.
For the previous graph that we did,
Yeah.
may you go back to it again, sir?
Yes. Let me redraw it here. Because I'm going to simplify it and I want you to point out where your issue is. Or we can go back. But let me try redrawing it here.
Yes, sir. I was just wondering what was the main ideas takeaway, because I just wanted to know to make sure that I'm following on the right track, since there was a lot of symbols. So just wanted to make
Right.
sure.
Yeah. So this is light power spectrum P, or P0. And this is the light power spectrum P. You know, the difference is that P has no sample,
Okay.
or the concentration of your analyte is 0, right? And here, you know, here you have concentration is not equal to 0, then this is power versus wavelength. Then we can transfer that into absorbance versus wavelength, right? And what this will look like is something like that, right?
Yes.
And so the main point here is that, let's say if the light, let's draw another copy of this where the light source is weak. Light source is weak. And we're still computing absorbance here versus wavelength. And then what we'll have is we'll have it will look like that.
Mm. Actually, the first one. Oh, sorry, I forgot to turn on my camera. So the first one essentially is the top hill, the top peaks, or the one with no samples is just a blank.
Mhm.
But when you have more samples, the P, what's the P stands for again, sir?
P
Transmitting.
is it's just light power.
Okay, so the light power goes down a little bit because there's more substance to absorb.
Right.
And then once you get down to the second graph, that is essentially, I just don't understand the second graph and the third.
Okay. Okay. So this is all is good. Right? But this could be if the light source is weak, right? So if there's a little bit of noise in P and P0, right? If there's just a little bit of noise in P and P0 here, what will happen is that when you ratio these signals, that ratio will oscillate wildly here. So if we have a signal that's, say, 1 plus minus 0.01, and we have 0.01 plus minus 0.01, right? This signal varies between 0.99 and 1.01. This signal here varies between 0 and 0.02. So if you try to divide by 0, then you'll get an infinite value, right? And so this is a problem. And so that could be like one of these peaks out here is they have a very low p value. And here you have a high p value. Or the corresponding P0 problem. The opposite P0 problem. So let me boil it down too. I'm not going to ask you such detailed questions about this on any exam, right? I just want you to know, like, if there's a lot of noise in either of these two spectra, then there will be noise in their quotient. Right?
So that is essentially the main ideas of this takeaway is that if there's noise in the main graph, then there's no when the quotients. Wait, what do we mean by the quotients?
The quotient. This is the negative log of P over P0. Log P over P0. So this here is a quotient. So if there's noise in P or P0, then there will be noise in the quotient. And if there's noise in this quotient, then the negative log of that actually can go to infinity, because the log of 0 is infinity, or is negative infinity rather.
If we start out with noise, the more we do with it, the worse it's going to get.
Yes. Exactly.
Noise doesn't go away; it just gets worse as you try to like manipulate things.
Exactly. And then it gets even worse if you tell your boss, because then you're in trouble. So it's, I mean, it's actually probably one of, I mean, I tend to go too slowly when I teach classes, but in this case, I'm going to say, screw it. Let's just keep talking about this, because it's actually an important question. It's a very practical, very real, very, it's a type of problem that's very frequently encountered. And it's just like, when can you trust your instrument? When can you trust the data coming out of it? And absorbance is a little bit of a weird animal, because you can trust absorbance then between about 0.001 and 2, right? You can believe those numbers. But if the light power through the blank is very low, then you cut the top off that. So let's say we have light power is equal to 1 plus or minus 0.01, right? Then P0, let's say a must be. P0 must be within what range to work with this P value? So obviously P0 has to be greater than 0, right? I'm sorry, this is P0, I'm sorry, and this is P. This is the blank, and this is the sample. Light power, right? So if the blank light power is 1 plus or minus 0.01, then the sample light power must be, well, first of all, it's got to be greater than 0, right? It always has, power is single-ended, it has to be positive. But sometimes the conversion into a readable signal will give us a negative value, right? And that's a red flag, right? You should never trust a negative power level, right? It's like a negative concentration. It doesn't exist. What do we say? Let me just take a quick side here so I can get a little feedback. If the concentration of let's say a molecule Q is equal to minus 0.015 molar, how would we describe that situation? Brandon, how would we describe that? See if Brandon's awake. Hey, Brandon. You're not muted, but I can't hear you, so.
I'm sorry, can you hear me now?
I can hear you now, yay.
It's kind of weird.
It's weird. Yes.
Yeah, sometimes it just doesn't work and it's really annoying. Anyways.
Yeah, it's weird and it's annoying. And the technical term is non-physical, right? That's a non-physical
Yes.
concentration, right? Because it can't happen in reality, right? So, so now, does that mean that absorbance, which is in theory epsilon BC, is that always greater than 0? And that's actually no. It should be. Absorbance should be greater than 0, but it's not always greater than 0, right? Because of instrumental noise, because of fluctuations. So if you get an absorbance that's negative, you have to discard it. You have to go back and remeasure your blank. You have to diagnose, you have to figure out what's wrong. There could be a whole range of problems, but if you get a negative absorbance, then you say, okay, well, this value must be discarded. So, for example, in this case, right, if we were stuck with this signal, what wavelength would we use to quantify the concentration? I would use, say, this wavelength right here, right? If I had nothing else to go on, I would choose a wavelength where the absorbance is not noisy, Does that make sense?
If you measure the absorbance of the blank to be negative, can you still just subtract out a negative and just say, oh, there's a calibration, something going on?
Well, so that's a good point, right? Because if you, the concentration of a blank is normally what we define to be 0, right? So now we can say, okay, this value is 0 concentration. Let's measure the absorption spectrum of it, right? Then what you're doing generally is you're measuring a power spectrum, the results from which can be are the great majority of cases, the results from which will give you positive values. But it's certainly possible to get negative values back from a computer or an analog to digital converter or something of that nature. Okay? So you can get negative power values back. And in that case, you must discard them because that's a non-physical measurement. You have to look and say, well, either we can't use this wavelength or we have to fix our instrument. We have to get a better light bulb or clean the optics or, use a different solvent or a different cuvette or a different detector or something like that. Does that make sense?
Okay, yeah.
Yeah, like there's a lot of possible solutions, right? And we don't need to know all of them at a given point, right? But we need to be aware that if we get certain values, if they're negative, we have to discard the information that we get. So I have a couple of points for y'all before we sign off. The first of which is what happened last time that now, last time we had 31 people and now we have 20.
Including yourself.
Yeah, right, including me. We have 20. So if you want to, you can write me an email and say, Dr. T, you're just a lazy bastard. And that's why.
Just that? Just put that in the email.
yeah. I mean, that's as an example, right?
You just teach a class at 7:30 in the morning.
That's also possible. And and the next thing I have to say is actually kind of important, which is that and this question for you: did you guys get an email from Kitty from the safety department asking you to sign something?
Yes.
Go to lab.
No.
Oh,
Yes.
No.
Didn't.
you didn't. Oh, okay. All right. So I have to figure out how to get her an updated list, because in order to take lab, which starts next week, by the way, and here's our lab schedule for this is Tuesday, the 16th. That's going to be Mina, whoever, Bento, Adam, Chiseth, Little, and Riley. It's going to be these 6 folks who are coming next Tuesday, right? And next Wednesday, it's going to be Kareem, Solomon,
I
blah,
asked
blah.
which doctor.
What?
I
Oh,
was
you
wondering
asked to
if-
switch.
Yeah, I
Oh
asked
my
last week.
God.
Yeah.
You asked last week. I know.
Okay.
So I wonder if anybody here can switch with Solomon for his Wednesday slot. Brandon, can you switch? Diane, Nicholas.
I don't think I can switch since I'll be here on Thursday with Polly.
Okay. All
Sorry.
right. No, that's fine. Okay.
Can you just add them to like the group B on Thursday? Looks like there's a space there.
can do that one.
That's actually true.
Do that one.
Huh? Okay. All righty. I will add you to group B on Thursday.
Wait, is group A on Thursday available or no?
Group A on Thursday is not available.
Oh, it's not available. It's full. Okay,
Yeah,
I'll just say group
because-
B then.
Okay, yeah, group B, that starts on the 25th. And it's the same experience, we get the same paltry 10 days or of lab or whatever, but
Thank you so much, doctor. I really appreciate it.
absolutely no problem.
Dr. Terrell,
Yes.
may I also be on group B for Thursday as well? So I'm originally group A on Thursday, but may I be switched to group B on Thursday?
Yes. Yes, you may.
Yeah.
Yes, you may. You like Solomon?
Because I have yes, and I have there's like some schedule conflict.
Excellent.
Yeah.
Okay, there we go.
Yeah.
There you are. There you are.
Thank you so much, Dr. Terrell.
Thank
Well, in that
Absolutely
case,
no
you could
problem.
put Solomon in.
So
Diane's
Solomon's
spot.
now Solomon's going to go back to A. No, just kidding. I'm just kidding. He's not going to do that. So let's see here. This is, yeah. So you will be in different rooms, however. I'm sorry about that.
Dr. T, so we
Yes.
do lab 1 week and the other week we off.
Yep.
it's-
Yep. 1 week on, 1 week off. And it's only for, and you have a total of, I think, total of 5 lab days, period. That's it. Sorry. It sucks, but actually I have to do a whole bunch more prep work for y'all because I got to get everything working perfectly so that you guys step in and everything works and you do your experiments. And then you go and you think, woo, we did instrumental. lab."
Dr. Terrell,
Yes.
so you're going to be in lab on these days, right?
Yes.
So will we not have synchronous lecture anymore?
Oh yeah. Yeah. So on starting next week, I have to go to San Jose State at 7 a.m. I have to give my lecture from my office, and then I'll walk across the hall to Duncan Hall. That's a good question.
So on the day we don't have class. So what should we do? We do the homework or just watch lecture online? Or?
You should plot the destruction of the world. Yes. You have to plan. You have to plan. You plan for world domination.
The world is already stressed, sir, with COVID.
I know. Maybe you just want to finalize your plans for taking over the world.
No.
Then, well, but you can make me your lieutenant.
No.
Does this mean Tuesday and Thursday lab people are going to be going to lecture in their cars? There's what, like 10 minutes or something in between?
No. So yeah. So there's going to be these 5 days when you have lab. You're probably just going to have to attend it. Just, if you want to, you can watch the YouTube lecture. Because
so, but we still would be meeting at 7:15 in lab or 7:30 in lab.
7. So Tuesday and Thursday meet at 9, and Wednesday meets at 7:30.
Oh,
I know, it is friggin' brutal. I do not know how this happened.
Are you going to be there on time, Dr. Terrell, or should we come like 30 minutes late?
I don't know. These are hard questions.
Dr. T, I have another class after your class on Tuesday and Thursday. Can I come to the school and take the lecture in my car and watch the lecture on my car? Can I go to the building and watch it? When we have a test?
You can come to the building, absolutely, no problem.
Okay.
Yeah. Once you sign that form that they sent you the email, and they have to send you the email, so I'll get back to Kitty. Then you can come in the building, no problem.
If we signed something last semester, is that close enough?
I don't think so.
Probably not.
I don't really know. Yeah, I don't. It
Hey,
certainly
Dr.
doesn't.
Terrell, before you close that,
Yes.
could I request to switch from Wednesday Group A to Thursday Group B?
Thursday Group B. Okay, sure. Who is this?
It's Kareem.
Oh, okay, great. Sure.
Hello.
Let's see here. Wednesday Group. There you are. So let's see here. To Tuesday Group. To Thursday Group B or Tuesday?
No, Thursday Group B.
Thursday.
Dr. Terrell,
Yes.
may I please?
You want to change?
I just want to switch to DH11 on Group B for Thursday. That's all.
What?
Well, I don't want to be
you guys are together.
Yeah.
You guys are together.
Please, that'd be greatly appreciated.
Oh my gosh. No. I'm going to make you pay. You have to wash my car.
What did I do? What?
You simply, Solomon, you have exposed a political weakness. Okay. I will release my finger if you promise to wash my car.
Yes, sir. We'll do.
All right.
Thank you.
I can help too with that.
That's all.
All right.
Professor.
Yes.
Professor, I have one question here.
Yes,
so
yes.
lab starts next week.
Yes.
What should we do before the first day of lab? Because I'm in the group that's going to be there the soonest. So I'm wondering what we need to have or what we need to do before we show up.
That is an excellent question. And I don't have a good answer for you right this second, but I will have one for you Thursday, and I will put it out on a notification to you. And we'll talk a little bit about how to prepare. It probably is going to be really minimal because I'll just have like some stuff ready for you. And I don't actually know exactly how we're going to divide up the labor. We got
Okay.
UViz, we got Raman, things like that we can do. And
Yeah. I just didn't know
It's-
if they were like pre-labbing or if I needed a lab code or whatever.
no pre-lab, no codes, nothing. Just we got to get that stupid email in. Otherwise,
Yeah,
they'll be
I got that.
Okay,
I have
that's
the
good.
email.
Good. Okay. All right. So hopefully they don't take me away in handcuffs. All right, guys. I gotta go, man, because I can't. I'm not allowed to keep you over. Okay,
Dr. Terrell, I
Brandon.
just wanted to remind you to come into lab.
Today.
Yeah.
Yes, I will see you today.
Okay.
Perfect. Excelente.
All right. Thanks, Dr.
All
T.
right. See everybody later.
Dr. Terrell, wait.
See ya.
Wait. Okay, what?
Wait. May I check in with you about the sapling thingy?
Let's talk about that over email after class. Okay. Okay, good. Excellent. Okay.
Yes. So did they reply back to you at some sort?
No. By email later. Bye.
Okay. Thank you.
Okay. Talk to you in a minute. Bye.
Oh, this is trippy. There's like 2 of everybody.